We're going to sketch this parabola from 5 key points. So if you think about the shape of a parabola, right, there you are, this U-shaped kind of thing. And if there's an axis on it somewhere, maybe like this, there's going to be x-intercepts here and here. That's 2 of your points. There'll be a vertex. That's 3 of your points. And there'll be some sort of y-intercept, 1, 2, 3, 4, which happens to have a mirror point directly across the parabola from it. And with those 5 points, you can draw yourself a very accurate picture of a parabola without having to count every single step of the counting pattern. So we're going to start with our quadratic formula, which hopefully you have burned in your brain right now and will never ever be rid of it because it makes you wake up screaming in the night every once in a while. All right. If you recognize this front part here, this negative b over 2a, that thing gives you the x-coordinate of the vertex. Because when you're trying to solve for x-intercepts, you need to get to the center of the thing, and then you need to step up a little bit and down that same amount in order to get to those x-intercepts. So if I start with negative b over 2a, in this particular equation, my b value is 9. 2 is just part of the machine. My a value is negative 3. So I end up with negative 9 over negative 6, which is 1.5. Okay, so once you have your x value for your vertex, you can get the y value by just plunking it in here. So my y will be negative 3, 1.5 squared, plus 9 times 1.5, plus 5. 1.5 squared is 2.25. 9 times 1.5 is 13.5. Negative 3 times 2.25 is negative 6.75, plus 13.5 plus 5. That's 14. 14 less 6 would be 8, and 8 less 0.75 would be 7.25. Just fact check that. Come on, brain, you can do it. That'd be negative 13, negative 14. Yes, good, I agree. So, with a little bit of evaluating functions using this little key at the beginning, I found that there's a vertex at 1.5, 7.25. So I'm going to draw that in there, 1.5 on the x, 7.25 on the y. 7.25 is somewhere there, and there will be this axis of symmetry. Coming from that vertex. All right, so that's one of the 5 points we need to get. The y-intercept is really easy. It's just this number at the back. If you get y-intercepts by setting x equal to 0, so 0 this out, that term is gone. 9 times 0, that would be gone. All I'm left with is plus 5. So I can find that one. 1, 2, 3, 4, 5 right here. And the y-intercept will have a mirror point on the other side of the axis of symmetry. So this looks like it's 1.5 squares away, so 1.5 squares. I will have my mirror point. So all that's left is the x-intercepts. So I'm going to check the discriminant first. Let's see how many of them there are going to be before I get too carried away. So my B value is 9, A value is -3, C value is 5. That's 81, so plus 12 times 5. That's 81 plus 60, which gives me 141. That's a positive number. It's not a perfect square root. It's not a 0. So that means I'm going to get two gross roots. Gross because they're going to have a factor of square root 41 in them, so they won't come out as clean numbers. They'll be decimals. So fill in the rest of my quadratic formula and try not to write on my face here. Minus b would be -9 plus or minus the square root of 9 squared minus 4 times -3 times 5 all over 2 times -3. Make sure you get this part over the 2a as well. It's not just the radical part. Now I just did all this work here and got 141. So I'm going to have to pull out my little silicon friend here and figure out what the square root of 141 is. Which is 11.874. So I'll end up with two cases. X is -9 plus 11.875 over -6, or case 2. X is -9 subtract 11.875 over -6. Subtract 9. -6 gives me -0.479 and 9.875. 3.479. Okay, so I have an x-intercept at -0.5 right there, and I have an x-intercept at 3.5. So right there. Now with those 5 points, I am able to draw the round parabola nub and aim for that mirror point and aim for an x-intercept. Round off the vertex, hit the y-intercept. And with 2 tries, I end up with a pretty good picture of that parabola. Now, I didn't have to do any of the step patterning. I didn't have to worry about the transform factor or how to modify the 1, 4, 9, 16 pattern. I just needed these key points. And ultimately, when you're doing applications that involve anything parabolic, quadratic, there are 5 key places where it matters. If this was a ball being launched off of something and falling off of gravity, right? You throw the ball up, it reaches its maximum height, turns around, comes back down. Well, that point is important because that's where it was launched. Right? How high was the ball launched from? Well, that would be a question to answer, or they would have to tell you how high the ball was launched from. This point here, that's its maximum height. So that's a point to solve, or a point that you could be given in order to build this shape. This spot here, that's where it hits the ground. So at that spot there, you could either give that, or you'd have to calculate where this projectile is going to land. And that funny spot there, that would be the question where it says, when is the ball back at its original height? And that's where it was launched from. So they could either give you that, or you could have to solve for it. This little one back here, this other x-intercept would have been where it was launched from if it had been launched from the ground. So none of the other points in between there really have any physical meaning, and they are parts on the ball's path as it flies through the air, but they aren't the kind of spots where you actually need to know something about for an application. So these 5 spots, right, where its max min heights are, where it hits the ground, and then where it was launched from / where is it going to be when it returns to its original height, those are the 5 points that end up being used in all applications of parabolas. So you might as well be calculating them anyway and using them to make your sketch.